क्या हुआ, अभी और कोई आएगा, प्रवीण और आशीष, या बस?
Sir, Jeet and Komal are left. I'll call them.
Okay, I think we can start basically. It's already 10:23.
Okay, sir.
Yes, sir. The three people are. Let me share my screen. Okay, so I think let me check if can you hear me and can you see the screen?
Yes, sir. Yes, sir.
Okay, fine, good. So actually now, as you know, most of the background has been covered. Now, if we move towards slightly the polynomials, so I talked about irreducible polynomials, minimal polynomials, all those things you already know. So few results we need actually. So I am going to mention some of them, and you know just to make a note of them, and then few algorithms, then we can talk about it, and then we will move towards the actual thing. So let me so we are going to talk about polynomials over finite field FQ. So I think you know what is finite field, right? Field with Q number of elements. Okay. And also, you know how to find GCD, right? Just like that, integers, we have the greatest common divisor. We can, so FQ is if FQ is a finite field, we know that FQX is a polynomial ring where we can do addition of two polynomials, right? Subtraction of two polynomials, multiplication of two polynomials, right? So these things are there, right? Also, we can find the GCD of, so we know that we can define the greatest common divisor, GCD of two polynomials fx and gx, and we know that just like that we define GCD of you know integers. So polynomial rings means it is analogous to integers. You can think of so set of integers which is also a ring. So it works in the same fashion. So the GCD we can define, which is the same thing as GCD of gx and fx. Okay, and uh, you know we know that we can. This is nothing but ux fx for some polynomial ux plus vx gx from some polynomial ux and vx, or some polynomials in fqx, right? So this is something you know already. Now, I also recall one theorem. Of course, I have shown you in details about this. Today, I'm not going to go into the details, but I will just mention it. I say that the product of all monic means the leading coefficient is 1, irreducible polynomials in fqx of degrees dividing n is x raised to power p raised to power n minus x. Okay. More generally, for m to be a natural number, the product of all monic irreducible polynomial in fqx of degrees dividing m is x raised to power q raised to power m minus x. This is a general result. Anyway, so as an example, let me mention you one example here so that we know what we are doing actually. So suppose our prime p is 2 and n is 6. Okay. So all positive integral divisors of 6 are, so divisors of 6 positive ones are 1, 2, 3 and 6, right? So the polynomial x 2 raised to power 6 minus x factors over f2 as x goes to power 64. 2 raised to power 6 means 64 minus x is nothing but x plus 1, x square plus x plus 1, x cube plus x plus 1, x cube plus x square plus 1, x raised to power 6 plus x plus 1, x raised to power 6 plus x raised to power 5 plus 1 into x raised to power 6 plus x cube plus 1. Then we have x raised to power 6 plus x raised to power 4 plus x raised square plus x plus 1. Then x raised to power 6 plus x raised to power 5 plus x raised to power 4 plus x square plus 1. Then we have x raised to power 6 plus x raised to power 4 plus x cube plus x plus 1. Then we have x raised to power 6 plus x raised to power 5 plus x cube plus x square plus 1. X raised to power 6 plus x raised to power 5 plus x square plus x plus 1. And finally, x raised to power 6 plus x raised to power 5 plus x raised to power 4 plus x plus 1. So now I would like to ask you one question. Do you know how to find these factors? You can unmute yourself and tell your name and then tell me the answer. Do you know how to find these factors?
Yes, sir, using the division algorithm. We can first
Division
take
division algorithm, लेकिन note that now we are over finite fields.
yes, sir, but we can do one more thing. We can take x common and then for the remaining part we can get the factor.
So remember I told you about this minimal polynomial business, if you remember, factoring that x raised to power n minus 1, how we did it, right? और भूल गए हो? हमने आपको एक रिजल्ट दिया था ना, x raised to power n minus 1 का फैक्टर कैसे
Yes,
करेंगे?
the maximum powers of 1, 2, 3, and 6 divided of
Yeah, so I think that is the important thing. So I think this is an important thing. So in fact, how many? So basically, if I ask you a question, how many monic irreducible polynomials of degree 1 are there of f2x? Hmm? How many monic irreducible polynomials are there of degree? So I think I already told you about these things. So I'm asking a question: how many monic? Of course, I am asking for monic irreducible polynomial of f2x of डिग्री 1 आर कौन से होंगे?
X or x plus 1.
Good, 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 good. And what about if I ask you same thing for degree 2? How many monic irreducible polynomial of f2x of degree 2? डिग्री 2 में एक्स स्क्वायर तो आएगा ही आएगा, और उसके बाद क्या आएगा कोमल बताओ?
x square plus x plus 1.
वेरी गुड, हम लोग ये सब कर चुके हैं, राइट? यस, क्योंकि ये जो है ना, इससे ही तो हमने फील्ड जनरेट करी थी, फील्ड विद 4 नंबर ऑफ एलिमेंट्स, इफ यू रिमेंबर, राइट?
So,
एंड व्हाट अबाउट डिग्री 3? आई एम जस्ट रिकॉलिंग, डिग्री 3 के कौन कौन से होंगे? ऑफ कोर्स एक्स क्यूब तो होगा ही, एक्स क्यूब वो टर्म तो होगा ही, एक्स क्यूब प्लस एक्स प्लस 1 एंड दूसरा वाला क्या था? डिग्री, मतलब हम फील्ड विद 8 नंबर ऑफ एलिमेंट्स के लिए हमने 2 पॉलिनोमियल्स यूज किए थे ना, याद है?
Yes, sir.
x cube plus x square plus 1.
वेरी गुड, वेरी गुड। हम लोगों को सब याद है, थोड़ा सा टाइम लगता है रिकॉल करने में, बट विच इज गुड एनीवे। सो डिग्री 3 के ये हो गए, राइट? डिग्री 6 के ऐसे ही कितने हो गए? सो बेसिकली व्हाट आई एम आस्किंग क्वेश्चन, कैन आई फाइंड ए फॉर्मूला कि कितने मोनिक इररेड्यूसिबल पॉलिनोमियल्स होंगे किसी डिग्री के? एंड आई थिंक आई एम गोइंग टू मेंशन दैट फॉर्मूला नाउ, ओके? So suppose n qm is number of monic irreducible polynomial in fqx of degree m. डिग्री m के कितने मोनिक इररेड्यूसिबल पॉलिनोमियल्स हैं उनको हम nqm से डिनोट करते हैं अगर, तो बेसिकली थ्योरम जो भी हमने बताई है that tells us that, you know, what it says that, you know, if you look at the product of all monic irreducible polynomials in fqs of degree dividing n is this. So I can see how many of them divides the degree, right? So from that I can calculate. Here is the formula. One side we will be having p raised power n is equal to summation d divides n d times npd. डिग्री जो है ना, जो डिवाइड कर रही है, ये इस पे ये हुआ इस केस का, पहले केस का थ्योरम, जो पहले केस का था, द प्रोडक्ट ऑफ ऑल मोनिक इररेड्यूसिबल पॉलिनोमियल्स इन एफक्यूएक्स ऑफ डिग्रीज डिवाइडिंग n इज x रेज़्ड पावर p रेज़्ड पावर n माइनस x। जनरल अगर स्टेटमेंट लेंगे ऑल डिग्रीज डिवाइडिंग m, तो उस केस में वी कैन राइट इट डाउन जनरल वन, it will be q raised power m is equal to summation d divides m d times n qd. Okay, so the question is how do we find this value? Okay, तो डायरेक्ट रिजल्ट्स तो नहीं है, लेकिन थोड़े से ऑक्सिलरी रिजल्ट्स हैं which tells us how to find these things. So we can compute these functions in terms of some other functions, So let me tell you one such result. I'm going to define what is known as Mobius function. Mu from set of natural numbers to 0, 1, minus 1. तीन वैल्यूज पे जा रहा है, and it is defined as mu of n is equal to 1 if n is 1. So because there is no direct result, so this is something is interesting to note anyway. And mu of n is 0 if p square divides n for some p in the set of prime numbers actually. Okay, and it is minus 1 raised to power p if n is the product of t distinct pairwise primes. So depending on what is this factorization, Mobile's function value is this. So I think for small values, I can mention what is the value. So if n is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So mu of n, I can write it down. 1 minus 1 minus 1, 4 में 0 आएगा, 5 में minus 1, 6 में 1, 7 में minus 1, 8 में 0 आएगा, 9 में 0 आएगा, 10 में 1 आएगा, right? 11 में minus 1 आएगा, and 12 में 0 आएगा, and so on. So this is the Mobile's function, right? So function from natural numbers to this kind of characteristic, which is saying that it is either 0, minus 1 or plus 1. Okay. So now we have a lemma actually, which is an important lemma. So lemma says that now you can see that if we sum these values, the sum will be either 1 or 0, right? So if we sum Mobile's function where d divides n, so this sum will be 1 if n is equal to 1 and 0 if n is greater than 1. Okay. So sum is over all possible positive integral divisors of d of n, right? So let me look at a quick proof of this fact. Suppose n is nothing but p1 raised to power e1, p2 raised to power e2, pt raised to power et. Okay, it's a factorization for n greater than 1. Of course, we are assuming n greater than 1. Okay. And suppose the divisor d, which divides n, is of the form that d is of the form p1 raised to power r1, p2 raised to power r2, pt raised to power rt. Divisor होगा तो obviously is a product of some other primes, where of course 0 is less than or equal to ri is less than or equal to ei because वो उसका divisor है, right? Now if sum ri is greater than 1, then mu of d will be 0 by definition. Therefore, mu of d is non-zero. I can check when they are non-zero. Mu of d is non-zero if and only if ri belongs to 0 or 1. 0 means वो particular prime power नहीं होगी. 1 means that एक prime होगा, right? In that case, I can compute summation mu of d divides n will be summation over these ri's. So r1, r2, rt belongs to 0, 1 power t minus 1 raised to the power r1 plus r2 plus rt. Okay. So this whole thing will be, if you sum it, it turns out to be 1 minus 1 raised to power t, which is 0, right? Because ri's are either 0 or 1, right? So essentially we proved this result. Now there is another important result which is used, is known as Mobile's inversion formula. Okay, so what is this formula? It says that so f and g are functions from natural numbers to reals. So fn is summation over gd, d divides n for all n in natural numbers n. Okay. If fn is given like this, what about gn? And then gn is nothing but summation d divides n mu of d and f of n by d. Okay, in other words, this is nothing but summation d divides n mu of n by d times f of d. Okay. So I think a very small quick proof will be good here, since we have summation d divides n mu of d f of n by d, right? F of n by d. So it will be this will be nothing but summation d divide n, and we have mu of d summation d prime divide n by d, g of d prime. I have just substituted here. So this is nothing but summation d prime divides n mu of d g of d prime. We can actually separate it out now. Summation d prime divides n g of d prime, summation d divides n by d prime mu of d. So this is equal to, if I expand the summation, g of n summation mu of d d divides 1 plus summation d prime divides n, where d prime is less than n, g of d prime summation d divides n by d prime mu of d. Now using the previous lemma, this whole quantity turns out to be gn. Okay, so the inversion formula is this. So if Fn is given like this, we know that Gn is nothing but like this. We can compute. Now I think I can actually mention about this main result, the number of monic irreducible polynomials in FQX. This theory is little involved actually, but FQS of degree n is nPn, which is 1 by n summation d divides n mu of d e raised to power n by d, which is same thing as 1 by n summation d divides n mu of n by d times p raised to power d. And we can similarly mention the number of monic irreducible polynomials of degree m in FQX is nqm 1 over m summation d divides m mu of d q raised to power m by d, which is same thing as 1 by m summation d divides m mu of m by d q raised to power d. Okay, so this is the formula for number of monic irreducible polynomials of degree m in FQX. And let me give you a quick example so that suppose p is equal to 2, n is equal to 6, and I want to count how many polynomials are there of degree 6. N to 6 will be 1 by 6 mu 1 times 2 raised to power 6 plus mu 2 times 2 cube plus mu 3 times 2 square plus mu 6 times 2 raised to power 1. And when we do the simplifications, it turns out to be 1 by 6, 64 minus 8 minus 4 plus 2 is equal to 9. Okay, so there are 9 polynomials of degree 6. And I can mention them in all of them, I think you can find it out, all 9 polynomials. Okay, so this is the basic now I would like to checking the irreducibility. There is an algorithm I would like to give you. Algo for testing the irreducibility of polynomials. Okay. So the algorithm actually, what we know that suppose fx is a polynomial in FQX. It's a monic polynomial of degree d. D is greater than or equal to 1, of course. So fx is a monic polynomial of degree d in FQX. I want to check whether fx is irreducible or not. How do we decide? Okay. So basically what we do here, since we know that since x raised to power p raised to power so I think 1 minute. So we know that fx is reducible in fpx. In fact, I can take it q to be p to be, where is fpx will be a better one. Fx is reducible in fpx if and only if it has irreducible factor of some degree r, which degree is less than or equal to t by 2, right? Then it will be having a factor. So we know that x raised to power p raised to power r minus x is the product of all monic irreducible polynomials in fpx. So I will just check. I will divide and check now. Okay. So if it turns out that I compute the GCD of fx given polynomial fx with x raised to power p raised to power r minus x. If this GCD is not equal to 1 for some r less than or equal to d by 2, so we conclude that fx has factors, right? On the other hand, if it turns out that GCD of fx and x raised to power p raised to power r minus x is equal to 1 for all r is equal to 1, 2 up to d by 2. For all these values, if GCD is 1, then we conclude that fx is irreducible. Okay, so this is the basic strategy. Given the polynomial fx, we compute the GCD with x raised to power p raised to power r minus x, because x raised to power p raised to power r minus x is the product of all monic irreducible polynomials, right? So अगर fx उसका factor होगा, if GCD कुछ common होगी, right? So then if GCD is not equal to 1, fx has factors. If GCD is 1, fx is irreducible. Okay. So we can actually give now the algorithm here. Let me describe the algorithm first here. Our algorithm is, so given x of say fqx with degree d is equal to degree of fx is equal to d. This is given to us, right? And we know that its degree is equal to 1. We want to check the, so algorithm will give us the output whether fx is irreducible or not. So what we do, initialize a temporary polynomial tx is equal to x for r is equal to 1, r less than or equal to d by 2 plus r, okay, plus r. Set tx is equal to tx raised to power q modulo fx. Okay. If GCD of fx and tx minus x is not equal to 1, return false. That is reducible, right? Okay, false. Otherwise, return true. That is reducible. This is the basic algorithm. Let me give you an example here. Let me get some more space here. I don't know what is happening anyway. Example, suppose f of x is x raised to power 8 plus x cube plus 1 belongs to f2x, right? We want to check whether this is irreducible or not. So what we do, we take r and we compute x raised to power 2 raised to power r mod fx, and then we compute GCD of x raised to power 2 raised to power r plus x with fx. Okay. When r is 1, which is x squared, and GCD will be 1. When r is 2, this value is x raised to power 4, and GCD will remain 1, right? When r is 3, this value is x cubed plus 1, and the GCD turns out to be x cubed plus x plus 1. Therefore, fx has an irreducible factor of degree 3. Right, so I think let us do another example. Fx is equal to x raised to power 12 plus x raised to power 11 plus x raised to power 9 plus x raised to power 8 plus x raised to power 6 plus x cube plus 1 belongs to f2x. So I'm again writing the table. R x raised to power 2 raised to power r mod fx. This mod fx is important, and the GCD of x raised to power 2 raised to power r plus x comma fx. R is equal to 1. This value is x square and GCD is 1. Can you proceed with the other steps? R is equal to 2. This value will be x raised to power 4. And GCD of x raised to power 4 and this whole thing will remain 1. When R is equal to 3, this is x raised to power 8. And GCD turns out to be x raised to power 6 plus x raised to power 5 plus x raised to power 4 plus x cube plus x square plus x plus 1. That means we have found a factor of degree. In fact, this is reducible, right? Okay. One last example I would like to do here. So both for, we can factor them. So last example, suppose f of x is equal to x raised to power 15 plus x raised to power 4 plus 1 belongs to f2x. So now we want to check whether it is reducible or irreducible. So r x raised to power 2 raised to power r mod fx and GCD of x raised to power 2 raised to power r plus x comma fx, right? R is equal to 1, this value is x square, this is 1. R is 2, this value is x raised to power 4, this is 1. R is equal to 3, this value is x raised to power 8. GCD is still remain 1. R is equal to 4, this is x raised to power 5 plus x, because everything is modulo, right? GCD is 1. R is equal to 5. This value is x raised to power 10 plus x square. GCD is still 1. R is equal to 6. This is x raised to power 9 plus x raised to power 5 plus x raised to power 4. GCD is 1. R is equal to 7. This is x raised to power 10 plus x raised to power 8 plus x raised to power 7 plus x cube. GCD is 1. Therefore, since the GCD is always 1, now we know that GCD. So fx is irreducible. So this is a technique. Of course, it involves computation of the GCD. So the algorithm depends on computing the GCD, and that is how we can check. I think so. That's all for today. There are routines. I mean, you can write down a program in GP Peri GP to compute, to check the reducibility. You can implement this algorithm, and you can check it. And the complexity of this algorithm is actually, I should mention that the complexity is big O of d cube log 3 base cube. Because the loop in the algorithm, if I look at the loop, yeah. So this loop actually, the loop continues for a maximum of d by 2, which is order of d, right? Because this is d by 2 here, right? Okay, so this is order of d times. Each iteration of the loop involves a done modulo fx, that is the degrees of all intermediate products are kept at values less than d. The exponent is q, that is square and multiply exponential makes order of log q iterations only. Okay, so in short, each exponential in this algorithm requires order of D square log Q field operations. The GCD calculation involves at most D equivalent divisions, with each division requiring order of D square operations. So this is actually an overestimate. Equivalent GCD requires order of D square field operations. So arithmetic of FQ can be implemented in order of log square Q, time per operation. Okay. So essentially, that is you can calculate that overall complexity of the algorithm is order of D cube times log square. You can actually, by from the algorithm, you can do the things. You can improve this if you can improve the basic arithmetic, things. Because if you assume certain school arithmetic things, the complexity will be like this. I think that's all for today. Now we will be doing few more things in the polynomials, and then we'll talk about the primality testing things. Directly we'll give you the results. About the primality testing thing. Okay.
Okay, sir.
Okay. Thank you. Acha, by the way, have you done the assignment or not yet? Today is the last date, right?
सर अंडर प्रोसेस है सर.
तो क्या 1-2 दिन बाद दोगे या आज हो जाएगा या कल तक हो जाएगा?
सर पूरी ट्राई करेंगे आज रात तक कर देने को वैसे भी.
ओके, ठीक है. ठीक है,
सर
तो मैं कल
सबमिशन कहाँ करना है?
मैं गूगल क्लासरूम पे लिंक शेयर कर दूंगा व्हाट्सएप पे भी. गूगल क्लासरूम पे जो है ना सबमिशन करना होगा. ठीक है.
ठीक है सर.
ठीक है. ओके.
ओके सर.
Okay.
थैंक यू.